Hello, welcome to Linear Algebra with NumPy preview videos. In this video, we're going to talk about how to observe the matrix as an action with respect to different bases. So the difference between this time and last video is that last time we are observing a vector, but this time we're observing a matrix and considering that as the action. So in some earlier video that I say that a matrix like this has an action that multiplying this direction by 3 and multiplying this direction by 2. So if you have a circle here, then you will be stretched by 3 and stretched by 2, and it becomes an oval shape. But at that time, I just asked you to believe me that this is what it does. But now, let's try to learn how to build this matrix. Okay, the way is just try to observe this action in a different coordinate system. Let's try to do this as u1 and this as u2. Okay, now we have two directions and we can set up a coordinate system. And now let's observe this action again. This action is sending 1 copies of u1 to 3 copies of u1 and sending 1 copy of u2 to 2 copies of u2. So if you just observe the whole action and write down the corresponding matrix representation, then basically it looks like this, right? 1, 0 becomes 3, 0, and 0, 1 becomes 0, 2. And this is the big takeaway that we are going to say today, because if you use a different basis, then you can observe the matrix and get a different matrix representation. These representations are basically equivalent. They represent the same action, but sometimes one representation can look better than the other one. Now let's look at some technical details of how to compute such a representation. So let's say I have a matrix A. The action of that is sending V to AV. And so if I observe the whole action from the point of view of beta, and beta is an orthonormal basis, so I want the vector representation of V be sent to the vector representation of AV. And how does that work? We can use this diagram to achieve this work. Let's say we have a matrix Q. Matrix Q is a matrix whose columns are the beta, the vectors in beta. And we know how to transform the vector and its vector representation. So from the vector representation to vector, we multiply by Q. And then we multiply by A to get to AV, and then we use the Q transpose to get into the vector representation of AV. So the whole action is Q times A transpose, but it's multiplied from the right-hand side to the left-hand side. So this matrix representation has this form, and equivalently, you can also write it like this. Now let's look at some code and look at some example. Let's say we have a matrix A and a matrix Q, and notice that this matrix Q, each column are orthogonal to each other, and we normalize that by its length. So it's an orthogonal matrix. Q is an orthogonal matrix. Now we can calculate A beta, and this is the following the formula we have, which is the matrix representation of A with respect to these 3 vectors. So it turns out that this matrix representation looks like this. This is the output, and we can read it from this output, and it says that if U1, U2, U3 are the 3 columns of Q, then U1 will be sent to 1 copies of U1, U2 will be sent to 1 copies of U2, and U3 will disappear. So the whole action is like U1, U2 will stay the same, and U3 will collapse. So in the end, this action tells us that the A is a projection matrix onto the space spanned by U1 and U2.